Welcome to this video lesson, which is the full solution to the practice questions from lesson 19, which focuses on angles between a line and a plane and angle between two planes. The first question here is in two parts. We want to determine between the angle for part A between two planes that are both given to us in the Cartesian form. We can find a normal to the first equation here that will have components that are the coefficients of x, y, and z. So for the first one, we get 3, 2, and -1. And for n2, the second vector here, our components are going to be 4, -3, and 1. And again, those are the coefficients of x, y, and z. Once we have this, we need to find the magnitude and the dot product, magnitude of each vector and the dot product of them. So write the final equation here. So cos theta is going to equal to the magnitude of the dot product of the two divided by the magnitude of the normal of the first equation and the normal of the second equation. Okay, for the dot product of the two vectors, we got n1 and n2. We got 3, 2, -1 dotted with 4, -3, and 1. What we are going to do is we are going to multiply their x, y, and z components together and add them up. So we will have 3 times 4, which is 12, plus 2 times -3, which is -6, plus -1 times 1, which is -1. 12 minus 6 is 6, minus 1 is 5, and that is our dot product. So this is going to equal to magnitude of 5, which is just 5 divided by. Let's find the magnitude of n1. That is going to be the root of the x component squared plus the y component squared plus the z component squared. This will give us root of 9 plus 4 plus 1. 9 plus 1 is 10 plus 4, it is 14, so that's root 14, so that will go right here. And the magnitude of n2 is going to be its x component squared, which is 4 squared plus y component squared plus the z component squared. This will be 16 plus 9 plus 1. 9 plus 1 is 10 plus 16. It is root 26. So now the theta is going to be the cosine inverse of 5 over, we can multiply these out, or we can just write it as is. And once we put that on our calculator, we will get that the acute angle between these lines is approximately 74.8 degrees in 3 significant figures, and that is our final answer here. For the second part of the question, we're asked to find and determine the angle between a line and a plane, and for this, the equation is slightly different. We need the vector or direction vector here, let's call it W, and we need the normal vector here, let's call that N. And that's components 2 for coefficient of x, coefficient of y is -4, and coefficient of z is 1. Once we have this, we can, I'll write the equation here, sine of the angle, let's use theta is going to equal to the magnitude of the dot product divided by the magnitude of the normal vector and the magnitude of the direction vector. Okay, let us do the dot product first. So the dot product n between the normal and the direction vector of the line is going to equal to, we will have 2, -4, and 1 dotted with 1, 5, and 1. We will multiply the x together, the y together, and the z together, and then add them all up. So for x, we get 2 times 1, which is 2. We get -4 times 5 for y, which is -20, and 1 times 1, which is 1. 2 plus 1 is 3, minus 20 is -17, so that's the dot product. Since we want the acute angle, we're going to get the absolute value or the magnitude of -17, which is +17. Now we need the magnitude of the normal vector. That is going to be a root of the x component squared plus the y component squared plus the z component squared. That's going to be root of 2 squared, which is 4, -4 squared, which is 16, and 1 squared, which is 1. 16 plus 4 is 20, plus 1 is 21. So we get root 21 down here. And for the magnitude of the direction vector of the line, we are going to take the root of the x component squared plus the y component squared plus the z component squared. That is going to be 1 plus 25 plus 1. And when we add them all up, we get root of 27, which goes down here. To find theta, we are going to take the inverse sine of 17 over root 21 and root 27. And when we do this, we will get that theta is approximately 45.6 degrees. And that is our final answer here. For the next question, we are to find the angle between the two planes, but this time our planes are given to us in a vector form. And we need to find the normal first, and that's the cross product of the direction vectors for both. So let's find the direction vector. Let's write them down first. For the first one here, the ones that are corresponded to parameter t is going to be 1 for I, -1 for or y direction, and for the z direction is +1. So those are the coefficients of the unit vectors I, j, and k. For lambda, it's going to be the same. It's going to be the direction vectors, the coefficients of the unit vectors for I, j, and k. So I'll write that in pink. We get 2 for x. We don't have anything in the j direction, and we got +1 in the k direction. For the next one here, we have the first one, we get components for x direction, we get +1. That's unit vector I, unit vector j, the coefficient is -1, and we don't have k on this one. And finally, for the last one here, we got coefficient of I is -1, j is 1, and k is 1. Now we need to find the normal vector. So for the normal vector for pi1, so I'll write that as n1, is equal to the cross product of the two direction vectors. So that's I, j, and k. And for the first vector, we got components 1, -1, and 1. And for the second one, we got components 2, 0, and 1. We're going to start off with I, or the x component, and we're going to block off the I component and do a crisscross. So these two multiplied subtracted by these two multiplied. So -1 times 1 is -1. minus 0 times 1, which is 0. So my first component here is going to be negative 1. Then we're going to move to negative j. And for this one, we are going to multiply these two and subtract them by these two. So we are going to get 1 times 1, which is 1, minus 2 times 1, which is 2. So 1 minus 2 is negative 1, and negative 1 times negative j will give us a positive 1 for this component. Finally, we got the k component, and for the k component, we are going to multiply these two here and subtract them by these two here. So we will get 1 times 0, which is 0, and we're going to subtract that by 2 times negative 1, which is negative 2. 0 minus negative 2 is positive 2, and that will be our normal vector to our first plane. We're going to do the same thing for our second plane. We're going to have n2 is equal to the cross product of those two vectors, so I, j, and k. And we are going to get the first, for the first vector, we got 1, negative 1, and 0 as the components. And for the second one, we got negative 1, 1, and 1. I'll do this one a little bit faster. We got for the x component, I'm going to multiply negative 1 times 1, which is negative 1, subtracted by 1 minus 0, which is 0. For the negative y component, I'm going to multiply 1 by 1, subtracted by negative 1 times 0, which is 0. And for my positive z component, I will do 1 times 1, which is 1, minus negative 1 times negative 1, which is also 1, giving me the three components for x being negative 1 minus 0, 1 minus 0 times negative 1, which is another negative 1 for y, and for the z component, 1 minus 1, which is 0. Now I'm going to shift everything up to here so we can see both of the normal vectors. And my final, not my final, but my equation for the angle is cosine of theta is equal to the dot product of, or the magnitude of the dot product of the two normals divided by the magnitude of normal 1 and the magnitude of the normal vector 2. Now to find the dot product, I will write both vectors. The first one is negative 1, 1, 2, and the second one is negative 1, negative 1, 0. To get the dot product, I will multiply their x components together. That's negative 1 times negative 1 is 1, plus the y components together, 1 times negative 1, which is negative 1, plus their z component together, which is 2 times 0 is 0. And this will give me 0. From this point on, we know that whenever the dot product of two vectors are equal to 0, that means they're at 90-degree angle, so we don't really need to go any further. If we did want to go on further here, we would get cosine of theta is equal to 0 over a finite value, which would mean that it just equals to 0, and therefore theta would be 90 degrees. Or that would mean that the two planes here are perpendicular to each other, and that would be our final solution. So we don't really need to go through and find the magnitude of n1 and n2 and plug them into here, because we would just get a finite value here, and when we divide 0 by any number, we would get 0. I've also gotten a picture of the two planes in GeoGebra, so I'm going to paste that in. I'm just going to make it a little bit smaller so you can see it. Right now you can see it nicely, but I'm going to just put it down here so you can see it. Again, I use the app GeoGebra to draw this. You can see I've kind of changed the rotation so it's a little bit easier to see. This is one of the planes, this is the other plane, and you can see that they're intersecting at an angle which is 90 degrees to each other. I hope that this video gave you some practice to finding the angle between two planes or finding the angle between a line and a plane. Thank you for watching.